Hi everyone, welcome to another ROS Q&A session. My name is Rodrigo, and today I'm going to be answering this question that I found on ROS Answers, in which this person, Jonna Verdonk, is trying to get the position of his Turtlebot 3 using ROS2, using transforms, and he's doing it on ROS2 on Foxy. So he's running a cartographer node, which is used to make a map using the LiDAR from the Turtlebot. And he's just having trouble understanding how the transforms work. So what we're going to do here is we're going to do a couple of things. We're going to first set up an environment, a Turtlebot 3 sandbox, if you will, where we're going to download all of the packages for ROS2 Foxy that are necessary to run the Turtlebot 3. And then we're going to replicate this issue by running the cartographer node and sort of looking at the transforms and how we can use these transforms in order to figure out where the robot is with respect to whatever world you're working with. And we're going to do this in a simulation. So let's start right ahead. All right, so the first thing we're gonna do, close this, is we're gonna do this in the constructsim.com, which is our platform. And you can create an account if you don't have one. And once you log in, we can go down here to my ROSject here on the left, and we're going to create a new ROSject. I actually already did one where I created this sandbox that I'm talking about, but I'm just gonna go, I'm gonna do it again so you can see step by step, and this is really useful because once you have this, you can replicate it in order to do all of the projects you want with the Turtlebot 3. That way you don't have to download the packages every time, and it just becomes a lot quicker. So we're going to choose our distribution, which is ROS2 Foxy, and I'm going to name it the same thing as I did the other one, Turtlebot 3 Foxy Sandbox. We'll just add number 2 here because we're replicating a ROSject that I made previously. And we can just put the description we want and just create it. And you can see it's been created right here, and it's ROS2 Foxy. So we're gonna go ahead and run it. And just while it's loading, let me just go back to the construct sim and just show you our platform in order for you to learn robotics. We offer a ton of courses and a lot of learning paths for you to get started with ROS fast. You don't require an installation, you can do it online, everything. And we have the largest ROS developer platform in the world. And we now have a real RoboLab where you can test your programs in these 2 real labs. So we have over 50 courses. So it starts from beginners all the way to machine learning and robotics theory. So I recommend you guys check it out and start learning right away. Okay, so now we go back to our ROSject, and these things, we're just gonna close them just to have like a blank slate. There we go. So first thing we're gonna do is to clone the repositories. So since this is a distribution Foxy, I was trying to follow a tutorial on how to do it for ROS2, how to download these packages. But there was an issue with this, especially this tutorial right here for its simulation. And this is because this repository that you're obtaining with this command right here, you can see, is for the latest galactic distribution. and it's not completely ready by the Robotics people. So that's why we're doing it on Foxy, because it's just a little bit easier. But that means that we're going to have to clone it a little bit different. So let me show you. And it's a little bit of a hassle. There's a bunch of errors that happen, so just bear with me, and if I make any mistakes, we'll just figure it out together. So first thing we're going to do is we're going to copy this in our ROS2 workspace. We're going to clone this in our ROS2 workspace. So as you can see, we already have some build and install and a log folder, and these are generated once you run calcon build. But I already ran into some issues with this, because there were some errors that happened because of these pre-generated directories. So what we're going to do is remove them, because anytime we run calcon build, it's going to be generated again. So it doesn't really matter if we don't have anything in there yet. So let's just remove it with this command. And you can see we don't have any more. So we're going to go into our src, and this is where we're going to get our repository from. And just make sure, like I said, you're using this Foxy Devil branch. So we're going to go here, clone it, copy the URL, go back to our ROSject, and just type in git clone -b. This is for branch, and type in Foxy Devil like it's called, and just copy the URL. Alright, nice. And we're going to do the same exact thing, except this one's going to be called Turtlebot3 messages and Turtlebot3 simulations. And now, like, we have all these 3 packages in our workspace, so we're going to compile it. So go back to the root of this workspace and type in calcon build symlink install. Let me see if this works on the first try. It's gonna take a while. So again, like I said, what we're gonna do is launch the ROS2 simulation for the Turtlebot3, run the Turtlebot3 cartographer to create the maps like this guy was doing, and we're going to open up RViz in order to look at the TFs and who's publishing what, and that way hopefully I'll clear up a little bit on how to use transforms to get the position of the Turtlebot3. Dun, 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 dun. Dun, 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 dun. I'm gonna put some elevator music in here. If I was good at editing, sadly I am not. But you can just imagine my Jeopardy or elevator music in here. Nice. Finally, 2 minutes and 28 seconds later. I'll probably make a cut there so you don't have to wait with me. But now it seems like we have everything, and like I said, look at this. These directories were generated again. So next thing we're gonna do is source our environment, and for that is source install setup.bash. And I also found these two important commands here. The first one is to specify the gazebo model path, and it's a little bit different in our case that this is, but first of all, we're not going to copy this echo and then these quotation marks, because this will go into the bash rc, and we're not going to put anything in there since we're in a ROS checked and we just want to keep things clean. We're just going to copy this, paste it over here, but let's make sure that the path is correct and our workspace is not Turtlebot 3, is called ROS2 workspace src, and it goes straight into Turtlebot 3 simulations. Let's just double check. cd ROS2 workspace src Turtlebot 3, and then simulations. There we go. Turtlebot 3 gazebo and models. So this is the path that corresponds to this one, so we're good. And then we're just going to specify our model. I think it's exported the same way as ROS Noetic. Yeah, but we're not going to use the waffle pie because we are lovers here of the Turtlebot burger. There we go. So now we should see the simulation working. So let's try it. ROS2 launch Turtlebot 3, and let's just double check with tab Turtlebot gazebo. There you go. We have these options. One I like to use all the time is this one. Oh, no. Turtlebot 3 world.launch.py. Great. So if no errors, we can go to gazebo here and this button down here. And we should be seeing the simulation here. Not sure why it's not showing up. Let's try and restart it. No, that's weird. That's strange. Let's try and launch it again because there's no errors. So this should be just to issue with gazebo startup. There you go. Like I said, it was probably the way gazebo was launched. Sometimes it happens. But there you go. We can see that here is our Turtlebot 3. Those blue things you see are the LiDAR. These are the scan values that the Turtlebot will be using to create the map. If you're doing, you're running the cartographer node right here, Turtlebot 3 cartographer node. And now we're going to look into our viz. Let's look at how it looks. Our viz 2. And click on this graphical tools button. There you go. So he is saying that map to Atom and then Atom to base footprint are being published. And when we go to ours, we see that map does not exist here. See, frame map does not exist. And he's using the actual real Turtlebot. We're using it with a Turtlebot. I'm sorry, with a simulation. But it would be the same case if you're using the real one. That map is not going to be published by Gazebo, by the simulation from Gazebo here. What will be published though is everything else, because the simulation includes a robot state publisher, and that robot state publisher will publish all of these here. So all we need to do is just switch it to, for example, base link. Oh, he makes a really good question about base link. So he's confused at what base link is, and there seem to be no transforms to base link. Is base link only used to get the relative distance between various parts of the robot, or is this also used for positioning of the robot itself? And the answer is no, it's not used for the position of the robot itself. It's actually base link. It's the frame that it's most conventionally used to just kind of specify not the middle, but like the center of gravity of this robot. So let's add the TFs here, and there you go. It doesn't have any names right now, and I was having an issue displaying the robot model, so I'm not gonna try. Well, let's try it, but I don't think it's gonna work, but it doesn't matter for our explanation. I'm gonna create an issue there for Robotics, because the description, when you include it, you can't really see the robot like in an earlier distribution, for example. But we have the TFs, which is what's important. So you can see there's a group over here, and there's one empty one here. So I'm gonna try and quiz you guys into which one is which. But okay, I'm gonna tell you. So usually this one is going to be Atom, so the odometry frame. So if I was to move the Turtlebot, you'll see this group moving away or moving closer to the odometry. And here we can show the names, and like I said, this one's odometry. So if we go here to the tree, and we can see that that's odometry. And let's just put two in: base link and odometry. Like I said, actually it's using base footprint. This one is the main one. Base footprint, base link, it doesn't matter. Once you have a transform from odometry to any part of the robot's TF tree will take care of itself. And for example, the base scan is where the scans will be. You can see it's a little further up. I don't know why I can't zoom in, so I apologize for that. So now we can see that the Gazebo simulation and in the real version, the actual robot will be publishing these two frames, base footprint and odometry. But what about map? So like this guy was doing, let's try and launch the cartographer node now. But there was one thing I wanted to show you guys in case you're doing a simulation like me. And if you're not, you can skip this part. So let's remember, we put everything in our ROS2 workspace. And we're gonna look for the cartographer package in the launch files. We're gonna use this launch file right here. So when we open it up and go down to the simulation time, we are going to, right here, use simulation clock if true. So we're gonna actually set it to true because we're using the simulation since these packages are made for the real one. So now that it's changed, we can just, we're gonna close this because that launch file actually launches RViz again. Doesn't matter. Oh, sorry, discard. And we're gonna launch, let's remember to source our environment in each new terminal we open. And let's launch that package. Sorry, that cartographer. It's called cartographer. And it's the cartographer launch.py, like this. Okay, and if we hadn't switched that clock time to gazebo, it would have been weird errors. So just take my word for it if you're using the simulation. And we'll see here that, there you go, this nice configuration is already set up for us, where you can see what's been created of the map already here in this gray kind of background here, the scan values, and you can still see the frames. So now we can actually look for this frame map. So let's go to the TFs right here. Let's deactivate all of them. Just turn on the map one here. So the map is actually right on top of the robot here. So now we see that the cartographer node is the one publishing the map frame. So it goes map goes to Autumn, and Autumn goes to the robot, the base footprint. So let's actually move it a little bit. So to do that, we can put our simulation here on the side and source it. And ROS2 run, I think it's launch Turtlebot 3 teleop. Yep. I gotta remember the name of the node. Teleop. I think it's teleop key. Okay, I'm gonna check. Sorry, guys. Turtlebot 3. Here it is, the Turtlebot teleop. It's actually a node, so it should be ROS2 run. And it's called teleop keyboard. There it is. Oh, shoot. We forgot the model. And let's just move it around a little bit so we can see just where the map frame is as opposed to the robot. Oh, this is fine. We can leave it here. We'll go to RViz, and you can see that the map has been created better, you know, because it's been looking at for more information from the scan. But now you can see that there is an autumn, a map, and just the group of, like I said, let's just leave base footprint because it's what we're interested in right now, like that. So we have this triangulation. So yes, now we can figure out the position of the Turtlebot 3 just using transforms. And so let me show you how to do that. It's really easy. You can do TF echo. So we're going to go to a new terminal and we're just going to do an echo between the frames. And that's literally what you got to do in order to figure out the position. So if you can't remember, I always just Google it, TF2 echo. And here's the receiving transform data. And you can put this into a program of yours, but we're just going to do it on the terminal so you can see it very clearly. So we can run ROS2 run. Should have read what it said. Let's just copy this. And it's between the two frames that you're interested in. So let's try from with respect to the map. So where is base footprint with respect to the map frame? And it's literally gonna tell us right here. You see a translation and a rotation. And this is from here to here. So you can also do from autumn, in case you're wondering how much it has moved from the autumn frame. But usually you want to know from the map frame. So usually it's this one. And that's literally all you got to do. And now you know that the robot at this moment, with respect to the frame map, is translated this amount and rotated this amount. And yeah, that's pretty much, oh sorry guys, that's pretty much how you do it. You can use this TFs in your program in order to figure out where your robot is from time to time. I usually just use the odometry message because here I'll show you real quick. But you can do it from TFs as well. ROS2 topic echo autumn. It's usually called autumn. There you go. So this is telling you how much has changed from the first moment. So you can see. I'm just gonna do one message because it's pretty annoying. Oh, you don't do it like this anymore? ROS2? I think it's maybe over here. No, it doesn't matter. So you can see, actually also you can see information for the twist and for the position with covariances. And this way you can include a subscriber to this instead of your TFs. That's what I would recommend, but that's not the question. The question is getting the position using transforms. And yeah, that's how you do it. I hope I helped you guys figure this out. And if you have any questions, make sure to put them in the comments down below. And we'll see you guys in a couple of weeks for the next video. And hope you have a good day. See you later. Bye.